welcome to the Crazy Hat Chemist. So today we're doing another video on bonding and molecular structure, so let's get moving. Bam! Okay, today we're going to be talking about the basics and polarity of molecules. Okay, I'm going to give you 5 different examples here to begin with, then after those 5, then we're going to do 3 more. Okay, so we've got a total of 8 examples. From this one lecture here, you're going to get the basics of polarity, how to determine polarity in molecules, and then from this, you're going to move on to other molecules and getting the polarity of all those. Okay, so here we go. Let's figure out how this molecular polarity is done. So the first thing that we're going to do, and we're going to do this in order, we're going to draw the Lewis dot structure for that molecule. Then from that, we're going to determine the dipole moment of each bond. We're going to draw that out. Then we're going to determine the symmetry of the molecule, and then from that, the molecular polarity. So in order for a molecule to be polar, 2 things must be happening, and that was on a previous lecture. Number 1, you have to have polar bonds. That's a dipole moment between bonds, or in a bond. Okay. Number 2, the molecule needs to be asymmetrical. So number 1, you need to have a dipole moment. Number 2, it needs to be an asymmetrical molecule. So if those 2 criteria are satisfied, then it is a polar molecule. If either one of those is not satisfied, then it is a non-polar molecule. So let's figure this out and we can go from there. So we're going to do CH4 here. The first one that we're going to do is CH4. There is the Lewis dot structure for CH4, which is methane, okay? And carbon is the most electronegative of these 2 elements at 2.5. Hydrogen is the second most electronegative at 2.1. So remember, when we draw this arrow here and we let that arrow loose, okay, the negative end, the tip of the arrow goes towards the negative electronegative element. Okay, and the positive end, where the feathers are hanging out, goes towards the electropositive thing, because that's positive. Hopefully you get that. Okay, so from carbon is more electronegative than hydrogen, so we're going to write the dipole moments of each of these. So actually the first criteria is going to be satisfied for determining the polarity of a molecule. Does this molecule have polar bonds? The answer is yes. Okay, that means that there's a difference in electronegativity between the carbon and the hydrogen, and I can draw this just like that. Now I need to figure out, is this molecule symmetrical or asymmetrical? If the molecule is asymmetrical, then after that, because it has polar bonds, it would be polar. If the molecule is symmetrical, then it would be non-polar, because both criteria would not be satisfied. So let's figure this out here. That is that shape of that structure there, right? It's a tetrahedral shape. Hopefully you got that earlier. So CH4 is tetrahedral. It has a dipole moment for each bond that's emanating from the hydrogen to the carbon. Okay, that is a symmetry in the dipole moment of each bond. Therefore, there is no molecular polarity and the molecule is nonpolar. So I'm going to show you this here, and you've probably seen this already before, but this is CH4. Okay, this is a symmetrical molecule. Okay, and because of that, this is nonpolar. All right, so we got that first one. Let's move on to the next one here. So the next one is right here. We're going to do the same thing, the same set of order, except for this one is chloromethane. That is CH3Cl. So we're going to first draw the Lewis dot structure. We're going to look at the electronegativity of each element. Okay, carbon has an electronegativity of 2.5, hydrogen 2.1, and now we've added on a chlorine here of 3.0. Chlorine is the most electronegative element, but it is bonded to the carbon. The hydrogen is the least electronegative element. It's bonded to the carbon. So let's draw that Lewis dot structure and take a look at this. Now we're going to draw the bond polarities of each of these. Okay, since carbon is least electronegative compared to chlorine, which is most electronegative, that means that the arrow goes towards the chlorine. And then, just like what we had before in the methane structure, that means that the carbon is more electronegative than the hydrogen, and those arrows emanate and go towards the carbon. Okay, so I'm going to show you this before I give you the answer, and then you're going to try to figure out what the answer is. So this is chloromethane. There's the chlorine in the green there. The hydrogens are in the white there, and the black is the carbon. So ask yourself, does this have bond polarity? Yes, because we drew the red arrows. That is a definite positive. So that's number 1. Number 2, is this asymmetrical or symmetrical? So is this side different than this side? Is this side different than this side? The answer is a resounding yes. And because it's a yes, this is polar. Okay, so check this out. Okay, CH3Cl, it's tetrahedral, right? It has a dipole moment. We have drawn those there for you. And it is an asymmetrical molecule. Because it's an asymmetrical molecule and it has polar bonds, it is a polar molecule. All right, we got that one done. That's number 2. Let's do number 3 here. By the way, that is the molecular dipole for the entire molecule. That's emanating through that carbon all the way through the chlorine. If we can draw that yellow arrow, it is a polar molecule. All right, that is the molecular dipole for the entire molecule. Let's do the next one here. The next one is CH2Cl2. We're going to be doing the same set of thing here. We got the electronegativities like we had before. We're going to draw our Lewis dot structure, and we're going to draw the dipoles of each of the bonds. Okay, remember chlorine is more electronegative than carbon. That's why the chlorine gets the tip of the arrow. Chlorine is more electronegative than carbon. That's why chlorine gets the tip of the arrow. Carbon is more electronegative than hydrogen. It gets the tip of the arrow. Carbon is more electronegative than hydrogen. It gets the tip of the arrow. So I'm going to show you this one, and then you're going to figure out whether or not this is polar or non-polar. Again, everything here on this set of 5 here are tetrahedral-like structures. So here's this one here, dichloromethane. Okay, hopefully you see that, dichloromethane. Is this side different than this side? The answer is yes. Okay, if you were to turn it like this, is this top end different than that top end? Answer yes. It's not a matter of cutting it right in the middle. Don't do that. Just look at one side to another side. You can turn it, you can twist it. It really doesn't matter. But it's asymmetrical and it has polar bonds. So therefore, because it's asymmetrical and has polar bonds, then you know the answer. And that answer is there's a dipole moment for that entire molecule. And being that there's a dipole moment for that dipole moment for the entire molecule, that means it's asymmetric and a polar molecule. Dang, got that. Okay, that's number 3. Let's do number 4. Okay, number 4, we're going to do trichloromethane. We're doing the same set of rules that we did before, no different. Okay, same electronegativities that we had before, no different. Now we're going to draw the dipole moment of each bond. Okay, here's the dipole moment of that bond, dipole moment of that bond, dipole moment of that bond. Notice the tips of the arrows are facing towards the chlorines and not to the carbons, away from the carbons. Unlike this next one, that arrow goes towards the carbon. Notice that I've also drawn these arrows heavier for the chlorines, and that is because chlorine is very electronegative. It has 3 sets of lone pairs of electrons around each chlorine. I haven't shown it on these Lewis dot structures because it really doesn't matter to do the bond polarity, but hopefully you get the idea. Now, can I draw a dipole moment for the entire molecule? So that is the question. So I'm going to pick this one up here and have you take a look at this. Do you think you can draw a dipole moment for that? Is this molecule symmetrical or asymmetrical? Okay, so dipole moment, oh, absolutely. Look at this end. With these chlorines, it's very electronegative, and you can draw that arrow that's from the hydrogen all the way through there. So this molecule has polar bonds, and it is asymmetrical, therefore it is polar. That is correct. Polar. All right, that's number 4. Let's do number 5. Okay, number 5 is carbon tetrachloride. Okay, carbon tetrachloride. We're going to do this one, same electronegativities that we had before. We're going to draw the Lewis dot structure for this. Okay, we're going to draw the dipole moments for each of the bonds. And then we're going to ask ourselves, looking at that molecule right there, is this symmetrical or asymmetrical? Can I draw a dipole moment for the entire molecule or not? So this is looking just like the first one. That is the methane, except that this time I have chlorines on the outside. But it's the same basic shape and structure. It does have dipole moments, but not for the entire molecule because this is symmetrical. So this one here does not have a molecular dipole and therefore is non-polar. Non-polar, baby. All right, check that out. Now we're going to do some other things here. Okay, so that was our first 5. We got 3 more to do here. Okay, structural isomers have the same formula but different physical arrangement of the atoms and therefore different IUPAC names. That's the International Union of Peer and Applied Chemistry. That's where we get all these systematic naming here. So we're going to draw 3 different Lewis structures for C2 H2Cl2. There are no resonance structures. So I want you to draw the structural isomers for this. So you're going to put the pause on this button here, pause the video, draw the 3 that I'm asking you to do, and then restart it. So here we are, restarting. Okay, so we're going to determine the molecular geometry, the hybridization, the bond angles, the polarity of all of these. Okay, so here we go. This is your first one, second one, and third one. They don't have to be in that order. They can be in any order that you wish, and it would be perfectly fine. Okay, so the first one on the left, looks like this. Okay, there's a double bond in between both of the carbons. Then these 2 green ones are the chlorines. These 2 white ones are the hydrogens. Okay, so we got to answer a lot of things. This is trigonal planar at this carbon. This is trigonal planar at this carbon. Bond angles of 120, like all trigonal planar structures. Okay, you cannot rotate this double bond right over here. It is sp1p2 hybridized. This is sp1p2 hybridized, no matter how you look at it. Now, the question is this polar or non-polar? Does it have polar bonds? Absolutely. We already did this kind of polar bond. We already did this kind of polar bond. So there's a dipole moment that goes from here all the way to here. So this molecule is polar because it's asymmetrical. Okay, the middle one looks like this. Okay, chlorines on the bottom, hydrogens on the top. You got that double bond. Hopefully you see that. This is actually the same structure right there. It doesn't matter if you had the chlorines on the top or on the bottom. And I'm going to do the first structure. It could look like that or like that. It's the same thing. Don't worry. Okay, so then this one here, the middle one looks like this. Okay, same hybridization, same shape, same bond angle, same everything, except for, is this polar or non-polar? Okay, we can draw a dipole moment going that way. This end is different than this end. That is most certainly polar. All right, now we're going to do the last one. This one here, okay, is like this. Now, either one of these structures would work perfectly fine. Okay, again, double bond in the middle here. It's trigonal planar. 120 bond angles. All that is the same. Okay, now, the dipole for this is going that direction. Dipole for this is going in that direction. So it's like pulling, but opposite. Dipole here is putting in. Dipole here is putting in. So it's pushing in. So they cancel each other out. That is amazing. So because of that, this structure here is symmetrical and therefore nonpolar. This is called a trans structure. So it's trans. Trans means across. Like transcontinental railroad. This is trans, which is across. The other 2 structures, I'm going to show those up here. The middle one is right here. This is cis. Cis means same side. Okay, this one is also cis. Cis is same side. Okay, so the 2 cis-like structures are polar, and the one trans structure is non-polar. Okay, hopefully that's working well for you. Okay, there is molecular geometry around each carbon, and that is trigonal planar. Molecular geometry is the same around each carbon. It is AX3. That's trigonal planar. It is 120 bond degrees. It's sp2 hybridized in all 3 examples. The molecular dipoles are right here, and there's no net molecular dipole for that trans-like structure. So therefore, the first cis structure is polar, the second cis structure is polar, and that third structure is non-polar. I'm hoping that I'm answering all your questions right there. Okay, you should be able to determine the polarity of molecules based on this one lecture. That is awesome. Okay, now I have one really super cool hat here that my son made for me. My youngest son made me this hat. Super cool hat. All right, check it out. Okay, if you like that video, give me a thumbs up, subscribe to my YouTube channel, and I'm going to see you next time for more cool chemistry videos. Bye now.